now is this is the last topic before we go into not differential equations, differentiation stuff. And for that, we need to understand what continuity is of a function. So before we so let's see. So I'm going to do some graphs and stuff, and continuity of a function at a point, let's say A. So when is a function continuous at a point? When the function's limit is the same as the value of the function at that point. So we're doing continuous. So this is our mini heading, continuous at a point, and point A. So how do I say that in math stuff? If the limit of the function as x goes to A, so we're all about points near A, but in this case, when we're talking about continuities, because you differentiate, when we do differentiation, if were you here last time when I did limit of a function? It doesn't need to be defined at that point A. But for differentiation, the function has to be defined at A. So that's the difference. So therefore, as x goes to A, so this is what is this thing here? It's a number. Limit of a function f as x goes to A is a number, and this number should equal the value of the function at A. And this is also a number. So these two numbers should equal. This is the definition of being continuous at A. Excelente, Sophia. So I would say that attending the classes on differentiation and integration would be cool. You'll get something out of it. You get the main two things about calculus, because until now, all we were doing was real numbers. And then we threw in some sequences. Now this is the calculus thing, and you can say, hey, we did look at some very simple stuff about differentiation and in this mathy way. All right, so this is the definition, and what I'm going to do is make graphs, 3 different graphs, and see if we can say about that graph that this function, this graph, is continuous at A or not. So our first graph goes like this. Here's our graph, and here's our A, and this is supposedly the limit maybe, or the value of the function. So this is all I have. So does this graph satisfy this condition? So let's see. The limit of, so this is our f. The limit of the function as x tends towards A from, let's say, both sides. So I'm going back to the old, this is one way to think about it, right? So this can be translated as x approaches A, does the function values approach L. If this is true, approach. If this is true, then the function has a limit. Or another way to say this is, what's the other way from last time? What can I put here rather than say as x tends to A? I can say we're thinking about all the points near A. How do we think about points, all the x points that are near A? We have to use this symbol because we're thinking about all the points near A means that their distance better be very close to A. So if A is here, we need to put a very small positive number here so that we can say that all the x's are within delta distance of A. And then how do we translate this into the abstract language of real analysis? This then becomes, if this is true, that all the x's that are near A, and since we didn't put this, means that x and A can be equal to 0. They don't have to be greater than 0. If they're equal, that means x can take the value of A, so it's defined there. That's what happens. If you put this here, this is saying that okay, anyways, that we this is saying we are considering A. I just thought about something else. And then here, what do we do? If this is the case, all the the x points that are near A, they are near A, which is the same thing as saying as x values approach A from both sides, then all the functional values will fall within epsilon distance of the limit L, or in this case, f of A. So I'm going to do both things here. So which this line or this line did I draw the picture for? This one or this one? These are the same things. This is the intuitive and this is the rigorous way of thinking about, folks. All right, okay, I'm going to change this. Let's see. How do I change this? I'm going to change. So this is actually right now, this represents the intuitive way of thinking as x, all the different x values as they approach this center point A, all the functional values approach L. And how do you say that in actually rigorous math so that you can do proofs and stuff and talk about this? You take this out and you say that if there is an open interval around A, and I'm going to put here what? Plus delta minus delta here in this open interval. So this is this open interval. All the x's map to functional values near L. How do I show that? So this is the first step. So here I replace the arrows coming from x from this side and from this side. Now all I have is little x's. All the little x's that we find nearby, all of them are defined because each one of them has a functional value. So now we're saying is we have a situation where if we look at nearby points of our center point A, all of these nearby points are there. If they are there, they're all defined. And if this is the situation, then we can confidently say that this situation will also be true. As in, all the fx values we will find for each one of these, the fx values will fall within this open interval. F of x, f of x. If we have this situation where all the x values that are near A, they map to f functional values within this open limit, then we are doing good, which means that this L is the limit because that's the definition. Okay, all right. Now, does this represents this picture here? Now the question is this function f continuous? So for that, our definition is this one right here. What's the value of this function when I stick a into it, according to the graph here? It's under, yes, it's a hole. So the intuitive idea is a graph of a continuous function is in which you never have to raise your pen. Here I had to stop, put a hole, right? Is now, if I have this here right now, is this function defined at a? Does this function have a value at a? Yes, because I just put this thing there. And that value is actually some number here. Let's call it m, for instance. Yes. Mm-hmm. So we will only be dealing with continuous function when we are looking at differentiation next Wednesday and Friday and so on for another 3 weeks. So when you're doing differentiation, you need to make sure that or at least at this stage, make sure that the function is continuous. If continuous means that the function, the point that we are interested in is defined as a value, and that value is the same as the limit of the function. If the limit of the function at a is the same as the value of the function at a, then f is continuous. That's the definition, which I haven't written down yet because I'm just still stuck here. What we're now looking at is functions, graphs of functions that are not continuous. This is an example of a graph that is of a function that's not continuous. So the question is, why isn't continuous? So it seems to have a limit or not. It satisfies this definition. What is this function's limit? L. L is not a functional value because the function is not defined at a. There's a hole right there. Okay, so this is true. The function has a limit. Does the limit of this function equal the value of the function at point A? And the answer is, this doesn't exist. Therefore, this equality is not there. Therefore, this function is not continuous. Or you could just say that, well, when I was drawing this function, I had to lift my pen. All right, next picture for this. Man, these are some of the ugliest. Because one of my heroes, he has these perfect. I'm like a messy, so messy because I only have one fucking whiteboard. I could use all of them, but the thing is, I would have to move this thing around. So I've got issues. I want to record this, even though nobody watches it. Oh, you do? Oh, thank you. Oh, excellent. I didn't know. Because I look at that, I'm like, is this why? Because I clicked on it. Does it have a view or somebody else clicked on it? And why have they watched it only for 1 second? Okay, here's another f function. And all right. And then we have the a. Remember, we're dealing with function continuous at a point A right now. Okay, now this is a function. Does it satisfy this definition? Does this function have a limit? Let's start with the easy one. Does it have a value? Does this function have a value at point A? Yes, right? Let's call it M. The other way to do that was, I did that, right? I put it here. So this function now is defined at, okay, let's go back to this one. This function is now has a, it is defined at A. It has a function value at A, which is M, but its limit value is, folks, this one. So I'm going to say f of A equals M. Is that true? Now, what about the limit of the function as x goes to A equals what? From the picture. M is the value of the function. Where does the function tend to? As the nearby values of the domain map to fx values that are within epsilon distance of the limit L. What situation do we have there? We have a situation where the value of the function does not equal the value of the limit. Therefore, this is not a continuous function, even though the function is defined there. So that's what I'm doing here, for instance. Does this function have this is L. Does this function have a value at A? Yes. F of A is what? Yes, very good. And then, okay, here we go. And then the limit of the function at as x goes to A equals what? Who said L? Yes, if you go from the left. So it has the limit as we approach A, or we look at points that are nearby from the left, then yes, all the function values seems to cluster around this limiting limit point. Therefore, it has, problem is it has a left left limit that is not equal to, Chris just remembered, because this one says, if we look at the points, nearby points from the right are, okay, so I'm going to put here L, and then the other thing I'm going to write here is the limit of x as we look at the nearby points at A from the right-hand side, then the function's value, the limit of the function equals M. Not M, sorry, L. I messed this up. This is L, and this is M. These need to be equal for the function as a whole to have a limit. It has a left limit and a right limit, doesn't have a limit, because these two, if they were equal, then it would have a limit. Therefore, this picture is telling us that the left and the right limit are not the same. And even though the function is defined at A, this side is okay, this side doesn't exist. This function as a whole doesn't have a limit. It can only have a limit if the left-hand limit and the right-hand limit were the same. Over here, the function is defined at A. The function has a limit L, but the values of, all right, so let's just go back quickly. All right. Why is this the case in this picture? Because f of A is, the function is defined, so is the limit. The problem for this picture is this is not defined. So we're already dead in water, even though this is defined right there. And here, this is defined and this is defined. That is not the problem. The problem is the value of the limit does not equal the value of the function at the point A. Because this is what? M, and M is definitely not equal to L. Are we still good? Are we run out of time? Okay, so we got another 15 minutes. No more, right? We go up to I don't even know when this class ends. It's not 2:05, but 2:10 or, and so Emma actually goes all the way to 2:15 and says the class is over. Okay, good. All right. I don't want to doubt Emma. She's the boss. Now, I had her in my poetry class like 2 years ago, my returning student. Chris, I've never known Chris before this class. I've got a student from California. He calls me constantly. I'm his father figure. Okay, now, he's a cool cat, the very smart dude. I think we're done here. Okay, let's move on. I think those were the cases. Yeah, I did that case over there already. Now let's go on. Yeah. Excuse me. So the most beautiful book on real analysis is called this, The Way of Real Analysis. So I would highly recommend buying this one. This is like the best textbook, I think. Once you know the material, it's very beautiful to read this. And it kind of, it's a lot of long passages of English. You know how they do that? Unlike the other books. So that's my personal favorite, at least for this week. Okay, now let's keep going. Why is it so up there? I can give you a free PDF. 200 and this country. The government should be subsidizing 149. Do I even have a copy? I just have the PDF. Well, I have all the books on my little stick. Like it's like you're looking at $1,500. What a fucking scandal, huh? Democracy is. All right, let's keep going. So here's our first definition. And this is the old standard definition you're going to get in textbooks. And then we're going to look at the epsilon delta definition, which we kind of saw just briefly. So here is a definition from a very ancient textbook. I'm not going to mention the authors here. A function f is said to be continuous at a point A. I'm going to underline that. In its domain, so what's the other business of continuity? So I'm going to say this here. So here we're looking at a function f continuous at a point A. The other way is, and we're going to get to that probably, maybe not today, but Wednesday for sure. F is continuous. If you want to think about a big chunk of the graph, right? What's a big chunk of a graph? How do you figure out a big chunk of the graph? You take a bigger chunk, right? We're taking the open interval around A to think about A. How do you think about that point A? If the function is defined, is continuous at A, you have to think about A's neighbors. And if A's neighbors are jostling around him, they're all defined, then what happens to the function value at those x's that are next to A? So it's always in context. When I say, when this definition is a function f is said to be continuous at point A, it's also all the nearby points around it. But the focus still is on the A. If they are behaving right, then the function values will also fall within that, right? And f is continuous on, let's say, a large chunk of the graph. How do you say that? You say it like this. F is continuous on the closed interval A comma B. So then what you're doing is you're doing this. You have a graph and you're saying, I want to know if f is continuous starting here, from here all the way to this point here. So I'm going to do this. So I'm going to put this. Here we go. So these are our, this is our, what should I put here? B or A? B. What should I put here? A. My question to you is now, I guess I'm skipping that. We're doing this right now. So f is continuous on the closed interval AB. Is it? We have to check whether what do we have to check? I have to cheat here. If it is defined at every point first, is the closed interval defined at every point, and at each point, so at each point is the functional value the same as the limit at that point? And the answer is, if I took this out, this function is continuous on this closed interval, because at each point, each point in this closed interval, the function value is the same as the limit. Then we go, what about the endpoints? So first, we do not consider, so for this to be true, you have to do this. You have to go, it is continuous. You have to check if it is continuous on the open interval AB. You exclude the endpoints and check for every interior point here. If each interior point has a function value which is the same as the limit value for that point, for this x here, then you have resolved that, and then you check for the endpoints. And then you go, and here, the limit value that we should be concerned about should be which one? Left or right? Because our concern is only, we're concerned about this chunk here, right? So these points are not available for us to even think about. We can only think about the nearby points coming from the left to the right endpoint. So in other words, we want to know at this point if the limit of the function as x goes towards this x here, let's call it, this is our endpoint B. B from, what do I put here, plus or minus? Left minus, very good. And this equals the value of the function at B, yes. So this is the second thing. So we have to check for if the limit of fx as x goes to the right endpoint equals the function value at the right endpoint. If this is true, and then the second thing we have to check for is this guy here. So this is A defined at, is the function defined at A? Does it have a value? Yes, so this exists. The right-hand side exists. Does the left-hand side exist? Does the limit of this function exist as we go towards A? From which side should we approach? What is not available? The nearby points that are available are from the right. This, whether it exists or not, doesn't matter. So therefore, we're going to put here what? Plus or minus? So we figured out that we need to know if this has a limit. Since this is not defined, we only care about this closed interval on the domain. So for us, the graph is just this much. This point, and then all of this, and then this point. So if you're going to figure out the limit, usually the limit needs to be, a limit of a point exists, if the left limit, the right limit and the left, the right limit and the left limit are the same. In this case, the right limit does not exist, because for us, this function just stops right there, because we've said we're only concerned about this domain. And in order to figure out what a limit of a function is, we have to think about the nearby points. So what is available is only these points here. So what's available to figure out the limit, if it exists for this, is only the right limit, because the nearby points to the right of this. So we put a plus here. This, it means right limit. This means left. I might have messed up when I was saying that. Okay. Did I mess this up, or this is right, right? This is the right hand limit that exists. This is the left hand limit that exists. So it's the left hand limit for the right endpoint. It's the right hand limit for the left endpoint. Just saying, just to add more confusion. But the fact is that we have to check for the endpoints separately, and then we have to check for the open interval. If every point in this open interval, every point in this open interval, it's a limit at that point exists and is the same as the function value of that point, then the whole open interval is continuous, bam, which is the case here. And then if these things are true, then we are done. Now, how do we mess this up? Let's say I put, now is it X, let's call it X14. Is X14 defined? X14 is a value in the open interval AB, and it is not defined. There's a hole there. Therefore, does the limit exist at X14? Both from right and left, same value. So the limit exists right here. Let's call it L. Limit exists, but the function is not defined at X14. In other words, if we stick X14 into the function, what are we going to get here? Not a functional value. It's going to be Kamla or Trump, undefined. Okay. Now let's go back to how much time do we have? 13 minutes, huh? This thing can continue. All right. Okay, so let's go back to where I was. So this was just a preview. Because the thing is, continuous at a point, and then you're like, well, what does that mean? And then what does that mean for the whole function to be continuous? All right. The whole function is continuous if it is continuous at each point. That's all it's saying. Tell me if it's continuous at every x possible in the function, every a possible. Millions of center points. Are they all defined and do all of those points, millions of these points, the limit is also exists. Then the whole function is continuous. Okay, so you just take this definition and expand it. Apply it to every point on the graph. So let's do the easy one first. What should I write here, folks? We're doing not the epsilon delta definition, but the old-fashioned delta. A function f is said to be continuous at point A in its domain if the limit of the function, what's missing here? I know it's afternoon, equals You will never forget any of this if you're paying attention. All right. And if you're not, then you will forget it. And the graph, we don't care about the graph. Now let's do another definition here, which is a function is continuous at A if A is, and another way to say this is this thing here. And I should put here. You guys seen this one? This is the one that we actually then use once we start looking at differentiation. So let's look at what this does is, what is this saying? This is saying all those functional values that are near L, for instance. And this is saying all the functional values near A, which is the limit. I could put L here, for instance. Now that would not work. This could be, okay, let's stick with that. All right, so I'm going to draw this picture. I'm going to draw a picture for this one here. And then I'm going to draw a picture from, and we're going to modify this picture so that, and so you have to remember how both of these look like and what they're doing. This is in, what is this saying? If this is true, then the function is continuous. If this is true, this equality is true, the function is continuous. All right. So let's draw a picture here. Here we have a function. Does it look continuous at, what's the center point here? Point of interest is A. Does it have, it seems like it's defined. Is this picture satisfactory? Should I add some, I could add some x's, right? X, 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 all these x's moving towards A. And then here, I could drop in, this is f of A. And then all the f of x values are. Okay, before I move on, what's the limit? What number represents the limit in this picture of this function f? Very good. Did somebody say that and I didn't hear it? Yes, very good. All right, next. In other words, that's our L, and it is also the value of the, okay, and is this continuous? Yes. Now, how do we do that? So we draw the same graph. Here's our A. So what was happening to the x values? X values were coming closer and closer to A. Here, how do we say that? How do we say that x values are getting closer and closer or are moving towards our point of interest? We want to know if this function is continuous at A. We want to know that as we go from the right, and in this case, we just do that, but we could do both sides. So we want to know is that as we shrink H, A plus H, let's say H is 3 right now. If I made A H 2, A plus H is going to get closer to the value of A because this is now 2. If I made H 0, we are looking at A itself. So these are A plus H here, then the second AH, A plus H, then the A. These are all the values that are getting, that are defined, and they get us. So let's actually, and right here will be, So all of these, as h gets smaller, a plus h becomes a smaller number, and we finally get to this one here. All right, folks. So I'll draw it here again. So what this is doing is that as h goes to 0, when we say h goes to 0, what are we actually saying? As x goes to a. I might have to do this again. Is this confusing or? Good. Sophia says good. Okay. What this is saying is that x is going to a. But we don't use x, we use that. And it depends on the book. Most of the time you're going to get this. All right. I think is there. Oh, yeah, we have to do one last thing. Unless we've run out of. No, we haven't, unfortunately. This class will never end. So I'm going to erase. That should be my slogan. This class will never end. The only hope for this class is if I die, because I'm teaching it again next semester. I was thinking I have different variations of this class. Super crazy, slightly off, solid. Okay. Oh, yay. Now we do definition of continuity. So this is our definition with the epsilon delta definition of continuity. F is continuous at a if for, what should I write here? For every, this is our given, for every, so we're doing delta epsilon, right? Delta epsilon definition. What goes here with the every? Epsilon or delta? F is continuous at a if there's a number delta and there's a number epsilon. They have to. Which one is the given one to us? If you remember from epsilon, very good. So for every epsilon, for every possible distance from the limit on your y-axis, you can make it smaller. You make that smaller, you have to make your delta smaller. You will be able to find there is, as in there exists, there is a delta, which will then define how big your open interval is on the x-axis. If this is the case, such that, so if you have those numbers, then f is continuous if for every one of the epsilon you choose, any epsilon sized epsilon you choose, this exists such that this condition is true. And the condition is if all the numbers that are within delta distance, this is delta distance of the center point A, the point we are interested in, this guy here, A. If we have this situation and this is true, then and then that's it, I think, unless I messed up. Nope. And I think I should forget about the A plus H thing. Like with this. Is this clear? Why? What is this? What happened? How do you rewrite this thing? This is the same as this. This is this notation. You can write this or you can say this in this notation, in the epsilon delta. If this condition is true, then f is continuous at A. And do I have to, I can draw the picture quickly since we have 1 more minute. So here's our graph. and here is our A. And then what does this say? If all the x's that are nearby A, nearby as in within delta distance of the center point A that concern us, then the limit exists if all the functional values f of x are within f of A, which is also the limit. And then here we throw in, so this is f of A plus epsilon, f of A minus epsilon. And here we have all these fx's. If these numbers cluster around here and they're all defined, then because they're defined, the functional values are also defined and they cluster around f of A or the limit, then then this function f is continuous. Which means that then we can do what? We can find out the slope at this point exactly, because we'll have all the things we need, which is that difference quotient. Then you take the limit of the difference quotient, and that is the derivative. Go seek truth somewhere else. In this class, we deal with lies. All right, that was a super lame joke. Let's move on. It didn't go anywhere. I love America. That's better. That's a good joke. I do love America, actually. I'm not leaving. Chris, you can go back to Europe if you need to. All right, guys. See you. Thank you for showing up. Your grades have just gone up because you showed up today. From A minus to an A. Yep. You got everything, Gavin? Very good. This was good. Oh, the A plus H. If you ignore that, then you're good, right? Or look at the PowerPoints, but that might be confusing. Sophia, you were super good. Yes. We'll be doing differentiation starting Wednesday. And then as soon as we finish with differentiation and the proofs and all of that, we'll do integration. And I'm actually going to give you the assignment next week. As soon as I'm done with that old one. Ask me. Also, the it is we're coming from the left, so it's a minus sign towards the right endpoint. And then for the left endpoint, we're coming towards the right. So the right limit needs to exist. Just here. I should not have mentioned right and left endpoints, then it would have been okay. You're saying for this A, it has to be because the only points available are to the right of it. So it's the right limit. Yeah. And you've done calculus before, right? Oh, this is really good if you're getting this. Very good.